Yes, we can start now. Yep.
Okay, good morning, everyone. Welcome to the first summer school organized by CNI. And we are happy to welcome Rahul. And he graciously accepted our invitation to be the inaugural speaker. And he will speak on online algorithms. So a brief introduction to Rahul. So Rahul is no stranger to ISC. So many of you might already be aware. He was a ME from here. He did his MTech from, sorry, at that time it was called M Engineering, right? In ISC in 2004, I think, with Professor Sundararajan, and then he worked with BSIM for 2 years, and then he moved to UT Austin for his PhD, where he graduated in 2009, right? As that I don't remember, so, but we overlap. So, and then since then he has he came back to India and he's been at TIFR, where he's a associate professor now. He has several best paper awards, and some of them I have it here. He had this Eurosip Journal on Wireless Communication 2011 Best Paper Award, and Best Paper Award at YOP 2020, and Best Paper Award Performance 2020. And he has numerous papers. He has written one book on random wireless networks by Cambridge University Press, which came in 2015. It's a very good book if you're interested in this stochastic geometry. And he's also writing a new book on online algorithm. That's what he's going to teach us in this summer school. So personally, I knew Rahul from my time when I was doing my PhD. So we had this first Winedale conference where, only 2 student speakers were allowed. And one of them was Rahul from UT Austin. And so I guess I've been following his career since then. And then I came back to India and I realized that he's already beat me to it. He was already a faculty here. So I went to visit him to, TIFR, and he gave me some inputs. Anyway, so it's a pleasure to have Rahul here. So without much further ado, please. Thank you. So do you need this mic, or I think it's another mic? Hey, for him, the scholar mic, right? My phone is not working here. Okay. Yeah.
Is it on? No. It's on? All right. So thanks, Parimal. I don't think it's on. Hello? Hello? Yeah, it's on. All right. So I forgot to work out in the morning, and these guys made sure that I was walking it as fast as I could to reach the venue. There was some tree fall on the way. All right. So thanks, Parimal. It's a pleasure to be here. I was teaching this course until last week at TIFR. So this is going to be a continuation of what I was doing until last week. So some logistics before I start. So there is, I made a Google Classrooms page for this. If most people must be familiar, the code is V for victory, Z for Zulu, R, Q, E. This is an O, not an 0. So if you, right now, if you go in, there are already some lecture notes and a lot of information already available for today's class. So what do I plan to cover in this course? So the idea was to do essentially 5 lectures. Each will be, 50 minutes of 2 sessions. And in between, we'll take a 10-minute stretch break. All right. So the plan is as follows. We'll start with an introduction to what we even mean by online algorithms. It's somewhat a different concept than what we are used to in this community. Then we'll go to one of the simplest problems studied in online algorithms called the ski rental. And this has been around for like 40, 50 years now. But even if you Google Infocom and ski rental, every year on year, you'll find different versions of it. So it still remains in fashion. Then we'll move on to something called bin packing, which is a combinatorial problem. Again, very canonical for these kind of objects. We'll go to something which is very familiar to all of you, caching without coding though. This is something also studied long ago before information theory community got to caching. Then look at rather method. We'll go to set cover problem, which is an example of covering and packing problem. So a primal is a covering problem, which dual is a packing problem. And these are again very fundamental objects. And finally, I'll go to online convex optimization, which is very much in fashion right now. So I've chosen these 5 topics. Primarily, these are more classical ones. This is the more fashionable one. And there is some common theme going around. So there are basically 3 things we'll cover in terms of concepts. One is a lower bound technique. Called Yao's recipe. So let me abbreviate that as Y. Then we'll look at something called a potential function method. And then we'll go to another idea, which is very important and powerful, primal dual algorithms. So people familiar with Lyapunov functions, this is a different avatar of Lyapunov functions, the potential function. So let me call this P and let me call this P comma D. So what is common between bin packing is we'll use P over here as well as Y. On caching, we'll use P and Y. Okay, sorry. This here. In the set cover, we'll use primal dual, and convex optimization will also use P. In ski rental, we'll use Y. So this is how I pick these topics to essentially illustrate these 3 techniques by using these 5 simple problems. So I'm hoping to finish all of this in 5 days. Depending on your feedback, either we'll get there or we'll stop somewhere in between. You have to shout. All right, I'll do that. I'll keep that in mind. Any other questions before we begin? So please feel free to talk. I want an interactive class. My objective is not to cover as much material and go away. I would like you to think highly about online algorithms by the end of it and would like to write one paper in that. And one interesting snippet that any problem you have looked at right now can be also extended to an online setting that I'm just giving a sales pitch now. And you can solve that in an interesting way. So keep that in mind, that how do I make my problem online and how do I solve it? So if you keep that in mind, thoughts will flow automatically. All right. Any questions before we begin? That is up to these people. So ask them. You don't have to write. I'll be providing all the notes to you. And they're in a nice enough form, I believe. Because they're supposed to come out within few months as a book. So they better be in a shape where you can read them. Any other questions? All. So one more announcement. Still one special prize at the end for the most engaging students. So now I don't want to define this. And faculty are out of it. So only students. Only students are eligible for one. I should write slightly bigger. Okay, I'll keep this in mind. I have used to having 4 people in my class. So this is already infinitely more than that. So I'll make sure. Any other question? So I'll announce that prize as well as the engaging student on Friday. So keep you guessing. All right. So now I have to drop my mic because I can't hold 3 things in 2 hands. All right. People on the. Okay. Fine. Sorry. I need my notes. So let's be. What is this big enough? People at the back. So let's start with a very simple case. So suppose you're given a vector of real numbers. X1, on x size, I ask you a simple question. Find me the value which is with how I don't care. All I'm asking you is find me the index I star or everybody can. Now let's model this as an online. So this is what we will call as the offline problem. Here I give you the full input X and you're asked to do some output and answer depending on the full input. Now let's try to make it up. Let 5 is 5. Some permutation. Could be identity, it could be whatever favorite one of your choice. Now input at time is the TF component from the left. From the left. So revealing one element at a time of Y, starting from the left. So all of this is here, and which is already part. So you don't have to write. Here I'm appealing to you not to write. Just split my notes from the course page, and everything is here. Now the constraint and script A give you a notation for an offline algorithm. And for an offline algorithm, I will keep using the word OPT, which is the optimal algorithm, which knows everything in advance. So the constraint works in as soon as it sees an element at time t, search y of t and declare it to be. Can I go below this? Is it visible? All that and declare it to be the best element. Remember, my objective is still to choose I star. That's my objective. But I'm getting information in a very complicated way. So at time t, accept the element yt and declare it to this element, and process stops. No more elements of y. All right. So if you make a decision that the tth element seen right now is my best element, I'm not going to give you any more elements to see thereafter. I'll stop right there. Otherwise, you pass y of t and demand y of t plus 1. But you cannot go back to accept y of t. Okay. So if you demand the next element, I'm not going to allow you to go back and demand, no, the previous one seen was higher, so let me change that. That's not going to be. These are the two constraints the online algorithm will do. Each time a new element is presented, either accept it, process stops. If you pass that element, you're not allowed to go back to the same element. Now think about it, or come up with an algorithm which can actually find I star under these two constraints. Right? So that's the whole point of it. That we're making irrevocable decisions. Once you pass on, I'll give you an example where this is highly spread. One great example is dating. If you're dating somebody, you break up, you got to go back to the same person. You can think of airline ticketing also. Today it's presenting your price, you accept the price, you book the ticket. If you pass the price, that price is not going to come back. No, not all. This is one way of setting up the price. It's going to extract the basic idea of what is the limited information which an algorithm is going to do. This is a great example. Why is chosen by somebody? Let's say, certain ones, but it could be arbitrary. Even if it is identical, still there is a problem. I'm just making sure that you can understand what pi stands. Some permutation of x is getting into. So if now think of an algorithm which wants to do this job. Can you come up with an algorithm? Even for a fixed pi. That's which will actually select pi star. This was a very easy problem in the offline world. You can always choose the largest element. You can shuffle whatever you want and always pick the one which is the largest. Now with this limited information, what can we do? We can. Yes, that's a good idea. Just don't think too complicated. Think of, is it possible to always select pi star? Just think about it. Which is always possible in the offline. Suddenly I made by this, you can say, contrived information structure. I want you to appreciate the difficulty of the problem. How easy or how hard it is now to compute I star, whichever algorithm. I don't care about the complexity of the algorithm. Pick up any algorithm. We'll try to see if we can succeed. So exploration is a good idea, but that will again require something. Some extra assumptions are required for that. What do you mean by accepting an element? Accepting an element is, I'm going to declare that element as my best element. And thereafter, I'm not going to give you any more elements which are relevant. Yes, I'm going to declare that as my answer. Yes, right. Mhm. There is no end. Problem is that. Sorry, say that. We can convert it in such a way that when the process ends, we give the events from the law, like that. Think about the problem. Like, yeah, now we can backtrack that. See, that's where the what you are like you've seen so far and what this is slightly different. There is no backtracking. As soon as you do this, the process stops. There is no other element even shown to you. And if you don't, I'm not going to let you go back and select something. Yes. Okay. So the decision is items seen so far and the current item. You can compare them in any which way you like. That's all you can do. Yes. Correct. At each time. Yes. Yeah, so that requires some assumptions on pi. If I keep pi arbitrary, that also will not. No restrictions on how much you can store. No restriction on the complexity of the algorithm. That's all. But then you're not allowed to go back. If the best element happened to be the first element, you're not allowed to go back. But that doesn't mean that you're picking the largest, right? Because somewhere you stopped. There could be another element which is even larger than that. No, I'm not saying that what you can. Yeah, think about for the moment an algorithm. Can it select I star? Just think of that. We're not going to talk about algorithms. The goal to select I star. For the moment, goal is to select I star. There are other formulations where you can go close to the value of I star. That's another way. For the moment, I give you binary reward. To select I star, I give you one. That's all. Sorry, you cannot choose product. That's somebody else is choosing input. You can. That's the whole point. You actually don't know what these elements are. Think about it. Somebody is giving you some partial input and you're making certain decisions without knowing what actually is going to come in future. Think of dating problem. So you can be very right. Answer is correct, but you can't actually do that. If I don't make any assumptions on pi, there is no way. The inputs are very easy to construct inputs. So essentially think of an input which just keeps increasing. Think of an input which is 1 beta plus to the n minus 1. Where beta is some quantity greater than. Suppose this is the way input is coming. Either you stop somewhere and declare that to be bigger, but then you're losing because the next element is still bigger than that. Or at this point, you say, okay, I don't choose anybody. At this point, I will give you one. In which case, again, you're losing because this guy is the biggest. No matter what you do, unless I make some assumptions on pi, will bound. This input clear, why it is going to fail? So any algorithm will stop somewhere. Say, okay, this is my best element. The next element is only bigger than that. Let's stretch it all the way to the n minus first element. At which point it is beta to the power n minus 1. Now you say, I don't want to select this also, hoping for a even larger element. Because if you see any machine learning algorithm, they'll expect this to be growing even further. But nobody told you what x was. I can always give you an x where the last element from this 1. Now you're bound to lose because the only choice you're available is 1, which is much smaller than beta. So in this setting, without making any assumptions on pi, you're bound to fail. So this is not a class on this. So this problem is called secretary problem for many different reasons. You can call it a dating problem. I think that works much better with young people. And you need some assumptions on pi for this to work. So we're not going to actually find time for them. So you don't need any statistics. All you need is pi to be uniformly random. That is all. So suppose x is chosen by an adversary. So the element values are chosen by an adversary, but pi he doesn't control. And the order in which these elements are inputted are uniformly random. That's good enough for an algorithm to make sense. Then your exploration algorithm. So you observe certain number of values, and then once you build up some kind of a threshold for it, the next better value than that to select, and then algorithm. So this example is just to exhibit the difficulty an online algorithm works with. And the reason for doing this course is that even under this difficult input setting, for many of the problems, we are able to get something useful. This is not one simple. There is no infinite, so there is no limiting argument anymore. You can just think of this as n being known or unknown. The input level is going to be n. Many cases we don't know. This particular problem we need to know one is. But in general, the kind of problems I'm going to talk about, you do not need to know what the length of the input is. Doesn't help. I just give an example. That knowing it doesn't help. Algorithm is working under a constraint. Algorithm is on it. So an algorithm which works under these constraints is called omni. I can get the exact answer. No. But the probability is the all right. So hopefully the information structure is good. So let's look at another setting where it is y to some values, y quickly lengthening. What am I given? I am given it's called the offline setting. What I want to do is to partition y as the Suppose one partition is Pi, behind Yj belongs to Pi. To satisfy the summation the question from yes. This is an online interview. Cases where the objective is to find I star in the R something of f of xi, whereas it is non-linear. Yes. So whatever works without the f wrapped around it will work with the f wrapped around it. So here without so f being identity already there is a problem. What do I want? I want partition these. You can think of them as mates. As fewer number of partitions that is somewhere in each partition is less than equal to. That's what I want. So think of your boxes which can handle total weight of at most one. Each value is some value between 0 and 1. And you want to use as fewer number of boxes as possible. So again, in the offline setting, is it easy to find this? The offline setting is I give you the full set and ask you to solve it. No, don't worry about math. Is it possible to do this or not? Okay, what is one possible algorithm? I'm not giving any constraints on polynomial time, nothing. Everything is for free, right? Just give me an algorithm which you do my job. Yes. So that's not the fewest number of them. I want to output an answer which requires the least number of parts. I should use least number of boxes. Suppose box costs 1,000, but you do not like to spend on it. It's not only one. Even in the offline setting, it's actually a NP hard job. But I'm not asking you to put any complexity restrictions. Complete enumeration. That's completely okay for me right now. See, that's always possible. The exponential complexity. I don't care how you solve it. Once I give you these yi's, you can always solve this problem. I just want to belabor this point that problems in the offline world, we are not restraining them to have any complexity requirement. You can do as bad an algorithm as you want, but you can always output the correct answer. Is that point okay? So in the offline world, I can always solve the problem. Now come to the online. So similar to before, let's say Z is some permutation of pi, and at each time t, Z of t is revealed. Compared to my secretary problem or the dating problem, now I don't have to drop elements. All I have to do is a new element is given to me. I'm allowed to augment my current configuration. I'm not allowed to disturb my current configuration. Let's go back here. So suppose T is 5, 4 elements have already arrived, and I have used, let's say, 2 boxes. Let's call it B1 and B2. And I put in Y1 here, Y2, Y3, and Y4 are all sitting here. That's my current configuration. I've done these decisions in the past. And now Y5 arrives. Z1, Z2, Z3, and Z5 arrives. Now the online constraint is I cannot disturb what I've already done. All I can do is either put Z5 here, here, or open a third box and put a Z5. There are only 3 possibilities I have. This is another way of meant the current configuration, you cannot disturb the current configuration. So it could be that the optimal answer, once I see Z5, is to put Z2 back here and get Z5 here. It could be that might be the right answer, but I'm not allowed to do it. That's the constraint I'm going to work. So in this case, it turns out it's not too bad. You can actually come close to what an optimal algorithm can do. It's not as bad a situation as the secretary problem. Because here I don't have to throw away elements if I don't do something. I still keep them. I just make suboptimal decisions. Now coming up with some suboptimal algorithm which remains close to the offline optimal algorithm is not too hard here. So this is something we'll do tomorrow. We'll actually come up with an algorithm which stays close to the optimal offline. But is the information structure clear? What is the limitation an algorithm has? Yeah. It's not reducing the power. It's actually giving him the. That's okay, but that's as good as that, because what you could do is you could design an X in such a way that algorithm gets the input in the correct order in some sense, in which it would like to allocate objects in an offline setting. There could be a possibility of choosing one particular great pi for which an online algorithm can actually mimic the offline algorithm. So you want to take that possibility out of the, because certain inputs could be great. So another important point to remember, for a particular input, an online algorithm could actually match an offline algorithm. There is possibility. It's just that it has to match for every possible pi. That's where it becomes difficult. So you can think of it in as many different ways as you want. So pi essentially is capturing the fact that you cannot tune your algorithm to a particular pi. So that's another way of saying what you're saying. It's just a notational way of writing it up. No, what you are saying is exactly what we want to do. This is just one way of expressing that. So this should work for every pi. You can simply say, yes, it should work for any input. I'm just saying the same thing in a different language. We'll stay close to the. That's next. What is the metric we should worry about when looking at online algorithms? It's an important question. What is the metric we should look at? Any other question? All right, so let me just define an abstract online. With these two examples, I can do that. Yes. We don't get to choose pi. Suppose your friend who doesn't like you gets to choose pi. He'll give you a pi which doesn't work for your algorithm. And you have to design an algorithm which will work for every pi. Which constraints? These are also given to you by a designer, that your algorithm has to respect these constraints. Your algorithm which does not respect this constraint will not be called an online algorithm. So these constraints you can think of are the online constraints. We don't choose. This is so. For example, in the airline ticket problem, nobody chose, right? Today you go and look for a. Please give me the same price as you gave me yesterday. I'll book the ticket. The airline does not work that way. It gives you a new price. Now you can accept it or not accept it, not book the ticket. That's until complete under your control. These constraints are modeling real world problems. Okay, so this will be my input throughout the class. The input will be represented by sigma, the full input. Sigma with the superscript will be the prefix of length. Sigma 1, sigma 2, all the way to sigma. That will be my notation for rest. So A, which is my notation for an online algorithm, at step T or at time T, has information only about sigma t. That's the information it has seen so far. It has already acted on sigma t minus 1. It's supposed to act on the newest element. Makes a decision. The d of t at time t. And d of t is a function of all of sigma t. It can use what it has seen already. It's not required to only use the latest information. It can use all the information seen so far. And now let's call the cost of A as fa of sigma to be the cost it incurs by making the first decision, seeing the first input, d2 seeing the first two inputs, and so on until d mod sigma, sigma mod sigma. So this is the overall cost an algorithm incurs by looking at the full input, which is nothing but a function of what you did, the first decision made using the first input, the second decision made using the first two inputs, and the last decision made seeing the whole input. So it's some function of this. I'm just writing now in abstract terms. Is this comfortable? Sigma is my full input, sigma t is my prefix of that of length t. That's all after. So this clearly is observation or remark fa sigma depends on order in which sigma arrives. This is a loose language, okay? Sigma arrives. Right. I can make it more formal, but it's okay. So if point is that if I permute this input, the cost might be completely different. That's all the point I'm trying to make. While for offline algorithm, phi of sigma or sigma are equal. It does not distinguish between which input is the whole thing. You permute it, the input remains the same. So this is a major difference between an online algorithm. Let's come to the metric. What is the yes? This one, it sees the type to school. So all these are back to us, and you get some value corresponding to what you did. That's all. Decisions made at time t looking at the prefix. Corresponding to that, there is a cost. That is what I'm representing by f of all these decisions you made, combining all of them together. Yes. Yes. No, sigma is the full input, right? Sigma is my full long input. I don't even know what the length of the input is. For most of the cases, I would not know what the length of the sequence is. The machinery is powerful enough to handle that. No, we're not going to worry about monotone. We'll define a cost for a particular problem. Cost for my problem on the rightmost side is the number of bins you'll. Let me define that metric. It's not regret. Regret is a useful metric, but doesn't work for these settings. Right, but that's a 1-0 problem. So there are many different ways in which secretary problems formulated. One is what Nilesh was suggesting. Compare the value of the element chosen versus the value of the best element. That's one way of comparing it. you should already be thinking about that all of this looks hopeless. If you just see this much, you should really keep this in mind that no useful algorithm can actually come close to the offline optimal algorithm. That should be the first observation you should make from all this setting. This is information available to the online algorithm is so limited that there should be no way of doing something interesting. This is true if you allow your metric to be the regret. So now define, if you know regret, you know regret, otherwise you're not going to use it. So the metric for which it works is the following metric. We will define the ratio of the two costs. So FA of sigma, which I have defined over here, that's my cost I incur for the online algorithm. I'm going to divide by FOPT of sigma, where remember OPT is my offline optimal algorithm, which sees the input, it's the best decisions without any complexity restrictions. That ratio is what we're going to call. It's slightly making the job even more harder. Okay. So think of this as a minimization problem. That's why the max makes sense. So suppose you're trying to minimize the number of bins used to partition that set. This quantity will always be larger than this quantity because this is, you can, if otherwise OPT is not really OPT. And now I want to maximize this with respect to all possible input sequences. So not only my job is already hard here, coming up with an algorithm, but I'm also going to penalize you if for one bad input your algorithm does very badly. I'm going to pick that. So you have to be clever enough to handle every possible input in this universe you can think of. So this is called competitive ratio. So for a fixed algorithm, this is its competitive ratio. That how far in terms of a multiplicative ratio it is from OPT or all possible input sequences. For a maximization problem, there is multiple ways in which you can flip. My convention always is to keep the ratio the same. Just put a minimization, maximization. So whenever you think of maximizing an objective, you should think of this as your competitive ratio. Most often we look at the minimization problems. So this is what for you. On the competitive ratio. Looks like a hopeless object already. No. A sigma is the cost of A over the full input sigma. This definition. Where sigma is revealed one at a time. That's the only difference between OPT and U. So you should think of you sitting here, your adversary sitting here, and nature sitting here. Think of it that way. So ratios will still be meaningful. Even if this is going to infinity, we'll come to that where both are large, but the ratio remains. Sorry? No. That's not the only reason for this. Regret can be unbounded. That's the problem. If you know what regret is. Under this limited setting and worst case over the input, the regret could be arbitrarily large. You can't really control regret for most of the problems. That's why we don't look at regret. Yes. Can this not be unbounded? Yes, for a bad problem, it can be unbounded. Look at so one must question, why am I doing this? Like handicapping A, and then like he's already down and out, beating him further by putting a max around it. Yes. Yes. So that's the reason why I'm comparing, and I want this number to be as small as possible for an online algorithm. The best I can do is 1. Yes, it is without consent. That's the whole point, that even after tying his hands around his back, beating him for 2 days, still the algorithm will stand up. That's the point. So why adversarial inputs? Why worry about this bad? Why not of something which is more useless, more useful? Sorry. Yeah, but who is giving this bad input? You should always question that, right? Why can't you condition the input? Do something with it. Find something about the input. It's a superpower, agreed. But suppose for a problem it turns out very bad. Why should I worry about it? Or in general, why should I worry about it? The point is not powering. Point is that otherwise you need to model. Now, this is the difficult part. What is the alternative to this? Of some model about the input. Who is going to give you the model? Whatever model you think about it will always have some deficiency with respect to the real. So either you can say I'm robust. There are many ways in which people think about it. First, they model, they solve the problem. Then they say, okay, my model might be epsilon delta away from the real thing. So I'll also allow some kind of uncertainty ball around it and still tune it. This takes it to the furthest limit, saying I don't need to model, which is a difficult job. I will try to say, no matter what the input is, I will still design an algorithm which will work for all possible inputs. Now, this again setting would be useless if I can't come up with this algorithm which stays close to the OPT. The whole success of this area is that even after all this said and done, you can come up with algorithms which are reasonably good. The whole point. What it obviates is the need to model the input. It just completely neglects what the model is going to be. No reason to model it. Most of us did not come from this community. Most of us thought of models as some stochastic processes. And then either you do MDP or you do many other things. This is a completely different approach to that. It's a model-free approach. And not only that, it's worrying about the worst case. So alternatively, you can always say that for a probability measure of 0, there are bad inputs. Other than that, I am good enough. This is not even allowing you that. This is going to count even that one. That's not allowed. If you come up with an algorithm and claim it's good, I will go and find that particular input which is bad for your algorithm. All right, any more questions? And the second reason, so why compare against? That's another question you should ask. OPT is an ever powerful body. It sees the full input and is allowed to compute the optimal algorithm over the offline. Why should I compare this against this? This is too much if you think about it. You should really say online should be compared with online. I don't know the optimal online, but there should be some optimal online. Can somebody find a problem with that? If I do that, what problem will I face? If I were to compare my algorithm, which is one candidate algorithm, with respect to the optimal online algorithm. The problem is that optimal online algorithm also will depend on the permutation. So there is a problem in defining itself that quantity. That is why we go to the extreme end, choosing the OPT as our benchmark. So we are choosing the OPT as a benchmark, not for that we love it. It's just that there is nothing in between my algorithm and OPT which I can benchmark it against. It's everything is fluid in between. There is my algorithm, there is some optimal online algorithm which is difficult to characterize, or I don't even know what it means to say this, because that still depends on the permutation of phi. And then there is FOPT, which is to the other extreme. The best thing you can do, seeing the full input. And the reason to go there is not because I like it, it's just that I can't handle anything in between. So this definition really was for a deterministic algorithm. Now we should always ask what happens if I randomize. So a similar definition holds. So suppose you're allowed to randomize. So what does that mean? That input is still sigma. Now you act on sigma using randomized algorithm. So sigma t is revealed to your time t, your notation. So A produces a possibly random distribution. Now by randomized decision, what I essentially want to capture is that the adversary who's giving you the input doesn't have the control over the realization of the random variables this algorithm is going to use. It would still know the distribution that algorithm is going to use. So let me use script R just to represent a randomized algorithm. Now R is, if you think about, is a distribution over all possible deterministic online algorithm. That's the way to think about it. So you enumerate all possible deterministic online algorithms, pick each of them with whatever distribution you want. And that's what I will call this object a randomized online algorithm. Now that distribution is still available to the adversary when he's giving you the input. What he doesn't know is the actual realization of the coin tosses you're going to do. That's all he doesn't know. And that's going to give you enormous power compared to a single deterministic algorithm. Because now just heads and tails decisions possibly at time t, the adversary doesn't know if you're going to make a heads or a tails at that particular time, which will impact your decision. It knows the distribution with which you're going to toss the coin. So suppose it's not half and half, it still knows that you're skewed towards, let's say, heads compared to the tails, but that is all he needs. He doesn't know at that point what was the outcome of the coin toss you made. So that's the extra power you get by a randomized algorithm. And the competitive ratio for a randomized algorithm, let me call it R, is max remains as it is. Now it's an expected value of the distribution I choose over is, while my denominator remains the same. So input is not randomized, it's the algorithm which is randomized. So this adversary, which does not know, so adversary, or you can call it sigma, which does not know the realization of random is called the oblivious. There are also stronger adversaries, but we are not going to talk about that in this class. So this quantity, see if I pick, see this is one candidate. If I give all the mass to that particular A, this quantity, I'm only choosing something because I have the freedom to pick a D which is degenerate as probability 1 of picking that particular A. So I can do only better with this. Turns out that there is just one good algorithm, all bad algorithms. I should just choose that. But even there, it's very interesting that because the fact that I'm using multiple algorithms with certain probability, for each of these algorithms, there is a bad input. So think about it, that's where the nuance is. So think about that you have two online algorithms. Suppose the worst input for this is sigma 1. The worst input for this is sigma 2. Now the adversary doesn't know which A1 or A2 you're actually going to follow. So it has to hedge its bets between sigma 1 and sigma 2. And in the process, it might give something to the algorithm itself. If he knew it was A1, he'll always produce sigma 1. If he knew it was A2, it always produce sigma 2. But now the fact that you're randomizing between A1 and A2, it doesn't know what to do perfectly between this and this. So it might produce a third sequence which sits somewhere in between the performance of these two guys. And that is where the power of randomization. It can see everything. It knows the algorithm, it can see, it can simulate. It is deterministic, it can actually simulate the algorithm and give the input depending on what he knows you're going to do. That extra power you're taking away by randomizing. It precisely cannot simulate. It only can simulate on an average. Right. Time to take a break. And we come back. So the cost of OPT is simply min of L comma P. So knowing L is a very simple problem. What you don't know is, I don't know what L is, and you have to make decisions on the fly. Every day, decision. Yes. We're making it simple. Everything is discrete time. Every day morning, is the ski season going on or not? If it is, then you have to choose. If it ends right there. Then you don't have to go tomorrow or day after tomorrow. When it ends, it ends. Nothing. L arbitrarily large, arbitrarily small. What you know is P. P is known to you. How much? That is reasonable, right? You go out to a store, you should know how much to pay for a particular. That's all you know. You don't know what L is. Okay, and then what should I do? Yes. No, but that's a reasonable algorithm, right? What is he suggesting? Trying to mimic this somehow. Ideally, if you are new L, I would have done this. And if L was smaller, I would not buy. If L is larger, I would buy. And when should you buy? On day one. Because that's optimal. So similarly, if I don't know L, now I can predict either L is smaller than P or L is larger than P. There are only two possibilities. Now you have to keep safe distance from both of them. That's all an online algorithm is going to do. It doesn't know L. Adversary is going to pick a bad choice for him. So he cannot choose an optimistic choice for himself. So an algorithm will try to keep safe distance. This is loose language, but hopefully that point is clear that what safe distance means. That if suppose it is some number below, what should it do? It should just keep renting. And if it is larger than P, what should it do? Day one, the adversary will stop the season on day one. So that's too bad. The ratio becomes too large. It's equal to P. So it has to hedge its bet. So for the moment, think of deterministic algorithm. Don't think of randomized. Okay. L by 2. L is unknown. P is known. Okay. Why P by 2? Think of this tell you what number intuitively. Sorry? Mean of both. L is unknown. How can I choose? I know only P. I'm told I should stay in the middle. So I'll stay in the middle. Right. All right. Anybody else had a hand raised? No. So you're more or less in the right track. Just if you can complete the argument, then I'll write your. So the suggestion is to rent until -1 days and buy it on the period day if the season continues. And the intuition is coming directly from here. But why that should make sense. We'll do an exhaustive analysis just for everybody. That what happens if I go beyond, what else happens if I stay below P, what happens at P. But I want you to think about it before I go there. You're more or less there. You just need an argument why P should be out. I can even tell you that's the right answer. Now tell me why that is the right. We are the competitive ratio will remain 1 because OPT will rent, you will also. Okay, so you choose than P days. That's one thing you can eliminate. So suppose an algorithm decides I'm allowed to use any bad algorithm, right? So think of it as a bad algorithm. A bad algorithm decides I will rent until 2P minus 1 days and buy it on the 2P day. Can you argue that's a bad algorithm? Give me an answer why it's a bad algorithm, just so that I know what you guys are absorbing this definition. This is just not a difficult exercise, just to make sure that you absorb this definition. What are we trying to do? Okay, that's correct. And also tell me, suppose I pick choice of, so let me say K is my choice. That is rent for K minus 1 days and buy on the kth day. And I call such an algorithm a subscript K. These are all possible algorithms. A1, A2 completely characterizes all possible deterministic algorithms. So if I choose AK to be my algorithm, what is the adversary's choice of L? So you think of it as following. You choose an algorithm, adversary follows up on your algorithm, and then you choose, anticipating what the adversary is going to do, choose a K. That's another way of thinking about it. So you're choosing a particular value of K. What will be the OPT's response to this K? Because as soon as you buy, there is no incentive for you to get a free run. He should not allow you to see for any more days thereafter, because you bought it now. You paid as much as you could have paid. His objective is served by making sure that your cost is the largest. The same logic now, once you have for AK, the response of adversary is to choose L is equal to K. Now you can argue exactly what number, I forgot, I didn't get his name. Going beyond P days, going is not a good idea. Is better than going beyond P. But what if I stop before? That's also an option. K 1, 2, 3, all the way to P minus 1. That's also an option. Why is that not a good idea? Yes. No. So what will go wrong? That's an option, right? This is fine. That's the point. It's just that the ratio will turn out to be increasing function, decreasing function as you go from anything K below P to P. I'll write everything down. I'm just giving a sketch to what we should expect. I'll do this case by case analysis of all this. But I want to make sure that intuition is there, that there is something special about this Pth day. Right before the Pth day, you should stop. Like if you're still here, that is the ski season has not ended. This is the time to buy. And this applies to a large variety of problems, not just ski rental problems. Let's not go there. It could, but let's just concentrate on one metric we have. All right. Any other thoughts before I actually write down something? All right. So let's do case by case analysis. So AK is clear, right? AK is rent until K minus 1 days by on the 8th day if it is greater. That's my algorithm. All deterministic algorithms are some. So AK characterizes all deterministic for different okay, so let's say K is greater than P. So to this, what will the adversary respond? The two possible choices are this. Let's write this. This we have already argued. It will not go beyond k. Whatever the value of k is. If you are still not convinced, that part I'll leave for exercise. There's no reason for L to go beyond k. Let's argue it here. Okay, so what happens here? Just tell me what is mu of AK and mu of. You should be able to write this. K is greater than P, that I'm buying. I'm waiting until P crosses, while L is less than P. What would be my numerator and what would be my denominator here? Cost of OPT is always min of L comma P, right? So that is L. And this is also L because I waited. And L is P, so definitely add the L and A. So actually, so adversary is not value L, which is less than P. Beyond adversary is not one. Now look at this case. What is the cost of OPT when L is greater than P? It's just simply P. And what is your cost? You're going for K, which is greater than L, and K is greater than P. Where K is greater than P. So this is greater than 2P minus 1 by P. Let's write that. This much is clear. This much so far so good. Now what happens at K equal to P? You do the same analysis. You'll get mu K equal to 1 for the case above where L is less than P. This is identical. The only case remaining is K less than P. Now what happens? Can we say what happens? L is less than K or L is equal to K. In this setting again mu A is 1. Everybody is following? I'm not going too fast, right? I don't want to go too fast. If something is not clear, please stop me. It's clear if L is less than K, why is mu A equal to 1? Because I'm renting beyond L days, right? And I'm renting until K minus 1. And this is larger. So I also rented through all the days. So if L equal to K, what happens? I am buying while OPT is not buying. So I bought on the K day, which happened to be the season ending day. So I paid a cost of K minus 1 plus P, while the OPT paid only how much? K. Now you can compare the three choices and come up with the right answer. This is worse than this. So this is out of the picture. So the algorithm will not pick this. Because if it picks this, this is what it's going to get. So definitely among these two choices, always pick this choice. Only remaining choice is this. Now, what is this as a function of K? This is increasing or decreasing as a function of K? This is decreasing down as a function of K. So this is what this matches to. So if I end up choosing K equal to P, that's my optimal deterministic algorithm. So this is the simplest setting you'll ever find where we actually able to simply say by simple computation that here is my optimal online algorithm whose competitive ratio is exactly equal to 2P. Very rare that such a thing will happen. Otherwise, I have to do a lot of circles. First, upper bound the ratio with a converse. That is, no algorithm can be better than that, and hope that they match, which rarely happens. Is these simple computations clear to everybody? Yes. Think of any deterministic algorithm. What will it do? I'm not saying these are randomized algorithms. These are for deterministic algorithms able to characterize. Randomized algorithms can do many things. We'll come to that next. So any deterministic algorithm can be represented. This is another important point about this problem, that the characterization of a deterministic algorithm becomes very easy here. Because Otherwise, you can't index. There is a single parameter input. L is the only input parameter. And adversary cannot do much about L. In general, for problems we will see, input can be, depending on what you did, the next input could be completely different. So it can be an adaptive input. Here the input is really adaptive. And that is why we are able to write a simple indexing of all online algorithms. So also something kind of less interesting from this to observe is that deterministic algorithm is not very interesting for this problem. It's too easy to solve, so what's the point? So we have to, in the interest of doing serious math, we should look at more interesting setting, which is the randomized setting. And that is what we'll do next. Question really is that compared to this ratio, which goes to 2 essentially as p goes to infinity, how much improvement we can get randomization? That's the next question we want to ask ourselves. So any idea why should randomization even help? There are certain problems where randomization also doesn't help. So before we embark on saying, chalo, randomize खेलते हैं, is there a reason that it should help? No, that setting we know, but now you have to give me a concrete reason. What exactly will change? We agree that you cannot choose L depending on a particular choice of the algorithm you're going to make. That much is clear. But just because you're randomizing doesn't mean that you improve. There are problems where randomization doesn't help. So one announcement for the interest of our web audience. If you can shout or I can repeat. So choose any of the options. K or K. No, in principle, all of this is fine. I want a slightly more concrete reason. How will you actually do it? What materially will change if I random? In principle, all we know is randomization cannot be worse. Question is it strictly better or not? That's the question. Yes. Okay. That's true, but what should I really do? So think about all possible algorithms. Actually, you don't have to go beyond. We have argued that we should not go beyond P. So you should think of all possible algorithms as A1 through AP. Now you're putting some distribution. Let's say P1, P2. This is very, very bad. But let me try to differentiate between. So what is the randomized algorithm? Just choice of P1 through P capital P, which sums to. That's all a randomized algorithm is really. We saw that this was optimal deterministic algorithm. Now, if you want to confuse the input or confuse the adversary, you also have to give some mass to this. But equal mass doesn't sound like the right idea. Suppose I give equal mass to all of them. From what we have seen, does that make sense, or tell me the trend in which these PIs should change? More mass towards this much is clear, right? Because this is in fact the optimal deterministic algorithm. But if I choose only one of them, then the adversary can respond. So in some sense, there should be a decreasing sequence starting at P. So more mass here, but it should go all the way here. If you want to completely confuse the difference. If you stop here, he has power. So A1 is a reasonable one. Only beyond them is a bad choices. Yes, adversaries are always oblivious throughout my 5 days. it's a mess to deal with others. But there are very strong theorems to map one to the other. But let's not even talk about what they are. So at least an observation to make that Pj should be greater than equal to Pi for j greater than. Anything else what anybody wants to say? So let's take an example and to see before we go to the optimal random. In this case, we'll actually be able to characterize the optimal randomized algorithm also. But I don't think we'll have time for that today. Hey, you can do whatever you like. What eventually your goal is to find optimal probabilities. What you're saying is one candidate. Perfectly fine. I'll take these two candidates as my example. The example is a p by 2 and a p with probability half and half. Probability little p. So let me just to make sure. So this is my randomized algorithm. It only chooses two deterministic algorithms, one with probability little p, other with probability 1 minus p. And I'll try to compute how much advantage do I get compared to my 2p minus 1 over. This is a valid fact. It's not the optimal. I'm not claiming that this is optimal. So cost of, and let me call this R2. So only taking two choices, and it's a randomized algorithm, so I'm calling it R2. And sigma is nothing but the choice of L. So I also draw, so you can write it or you don't need not write it. This is equal to three possible values. One is then p by 2. It's little p, capital P by 2 minus 1 plus capital P is not magical. I'll just explain one thing. What am I using? I'm only using two possible choices for my online algorithm. One is a p by 2, other is a p. So is this clear? Why it is 1? Because L is strictly less than p by 2. So either of the two choices keep renting as the OPT does. So that remains 1. Now L goes beyond p by 2. That's when something interesting happens. So what is this cost? This is the cost of a p by 2, which happens with little p, probability little p. And this is the cost of L if I choose a p itself, which rents all the way as the OPT does. Is this clear? That L is between strictly less than p. So OPT is always going to rent throughout. My a p also is going to rent throughout. And that is chosen with probability 1 minus p. So that's the expected cost coming from a p by 2. So a p. And this is the cost. And now when L goes beyond p, the denominator is p, it just buys right outright. This should be. What is this correct? This is fine. It's 2p minus 1. This is what all possible values of this ratio is. Why am I not writing as competitive ratio? Anybody? I've written it as a ratio of the cost, not the competitive ratio. There is a max outside. I'm yet to do that max. So that's why I'm not writing it as a competitive ratio. Because now the adversary is allowed to choose L depending on what is going on. Now observe something at the third term. This is independent of L. Doesn't depend on L. And this is the only term which is dependent on L. Adversary will never give any L which is less than P by 2 because the competitive ratio is 1. So this is out of the picture. The value of L will be either this or this. Now here, what is the value of L adversary should pick to make the worst competitive ratio here? See this? Yeah, exactly. So this eventually boils down to 1 by putting L is equal to P by 2. This term is the largest. So you can simply replace this by P by 2 minus 1 plus P plus 1 minus P times over. And the third term remains as it is. All right. Now, can somebody tell me what should it do? Or what should an algorithm do? Algorithm should pick little value of little p, right? This is out of the picture. OPT is never going to, adversary is never going to give you this regime. Choices between this regime and this regime. Yeah. Let's suppose we did not even know that. Let's suppose. This should tell you something. See, suppose these are the two possible values of the competitive ratio. For any value of P, it's either this or this. So what should I pick a value of P so that, when does that happen? When this term is equal to this term. That's the only choice I've really got. At which time the adversary's hands are tied. He is indifferent to choosing an L between this value or this value because your cost is the same. If he chooses L P by 2, it doesn't matter. If he chooses L greater than P, it doesn't matter. All you need to do is to find P star such that these two values are equal. So for this example, it's easy to compute P star. So I'm not going to do this here. I know the answer. So I'm going to write that P star. All I'm doing is I'm equating these two numbers. They're both functions of P. One is going up, other is going down. So there is an intersection point. That's all. It's not a degenerate answer. So answer turns out to be P star is equal to 2 times P minus 1 over 5P minus 4. And supposing P is 10, what would be the answer for deterministic setting? 2 minus 1 by 10, which is 1 by 9.9. So mu AP was 2.9. Now in this setting with P star, mu R2 is equal to how much? 1. So just substituting it back and computing the answer. Nothing non-trivial happening here. So there is a significant improvement going from a deterministic algorithm to simply randomizing between two possible choices. I'm still left with the problem of solving for the optimum. Of course. Over all possible values here? That's not that easy. That's your assignment problem number 1 for today. How to do it directly, you need to do work much harder than that. So, and why do I call it a significant improvement? Somebody can say. No, I'm saying significant. It's changing in this first decimal place, that too by 0.2. I think it's significant improvement. I'm just saying improvement is significant. I'm not saying anything about the tightness of it. I don't know where I can go. I can go only. That is tight. I agree. Saying now by random. I would have also called this is acceptable. You are cut different to what I would not call it, but there is a reason why I call it. So I want that answer. Why is it still significant? See, for this problem is not accentuated. Typically what happens, because it's a multiplicative ratio or a ratio being taken, right? A ratio of 1.9 to 1.899 could completely change the answer. Because the OPT's answer could be 10,000, 20,000, 1 million, 100 million, I don't know what it is. And I'm going to multiply that with a number. Now that number being smaller in the third decimal place could completely change my cost. That's the reason we call any improvement a significant improvement. If it was an additive difference, I would not call it a significant difference. Because it's a ratio that because Google's revenue from web advertising is billions of dollars. And the algorithm they run, if you can improve that algorithm by the 10th decimal place also, you'd still make a lot of money for it. That's the reason we call this improvement significant. Now, I would have accepted this, but now I'm actually going from 1.9 to 1.7. So this is seriously significant. And how far I can go, we'll do that next time. I have 7 minutes to finish. That's your big picture, what to expect. So we're actually, so you will find the optimal PIs in your homework today. What I will try to do is an alternate way of proving the same thing. So one idea, which is a direct attack on this, to find PIs. So what is the expected cost of, let me just call it R, which randomizes over all possible choices. So all of them possibly are non-trivial, P1 all the way to P capital P. So this is equal to capital P. This is the cost of an algorithm. I'm even counting things beyond. You can eliminate those. That summation, I'm counting going beyond L also. There's just a superset of. What we know is that the cost of OPT is always min of L comma P. So what my objective is to minimize the competitive ratio. So I can solve the following problem. Infimize C. Is it visible? Subject to so this is a valid program for solving these PIs. Minimize the constant C such that the cost of my algorithm is at most C times the min of L comma P. Because min of L comma P is the cost of the OPT. And this is attackable. And that's what you will do if you attempt the exercise today. You can actually solve this. We already know what to expect here. There are many ways to answer that question, but we already know the deterministic algorithm is already doing close to 2. Then I can, using, oh, you want that C to be a function of P. Fine. Function. Exponent with constant. So if C turns out to be a function of P, in fact it is, only as P goes to infinity, it will turn out to be a constant. That constant is a magical number which will show up again and again and again. Which is going to be 1 minus 1 over E, where the E is nothing but natural, the base of the natural algorithm. All right, so now let me say that this should be perfect. Yeah. This is great. So what strong result? That comes very simply. So pay attention to this. It's too powerful for its appearance. So what I want to do is lower bound. People in information theory community might want to see it as the converse. Lower bound, the competitive ratio of any randomized algorithm. Any deterministic algorithm is simply defined. You can always come up with inputs and show that, okay, this deterministic algorithm cannot do better than this competitive ratio. That's easy to do. Saying it too easily, somewhat easy. This is hard. And that is why Andy Yao had this beautiful idea, which is very simply stated, but is super powerful. Let's call this a recipe towards finding a lower bound. So what do we mean by a randomized algorithm having a competitive ratio mu? It is simply that expectation with respect to D of cost of A sigma is at most mu times cost of for all sigma. This is just a definition. Mu is my competitive ratio I'm shooting for. So I'm saying mu is greater than this number. Everybody follows this. What it means? This is the D is over the distribution over all possible deterministic algorithms. That's the expected cost of a randomized algorithm. This is the cost of the OPT, and mu is my competitive ratio. I want some bound on mu. How small mu can be? Any ideas? What should I do? Something remarkably came up with. I don't know what this inspiration was. So rather than thinking of these bad input sigmas, what he said is, let's think of another distribution. Let's call it Q over the input. So be mindful. This guarantee I want for all sigma. This is being created from artificial object. Over the input, I'm going to create a distribution. I want to guarantee over all possible sigma. This in between object I am creating now. Can you make it more precise? Take a moment's thought. I think you're on the right track. Just take a moment's pause and tell me what you say. You guys are close to it. You're not saying what you should say. So think about a deterministic algorithm for this distribution of input. And think of the best such algorithm. Can that tell you something about a lower bound? So fix the input distribution Q. Best deterministic algorithm. So what can I do? No. That's too much. It's way too much because I don't know what all possible distribution I have to handle. So I'm just going to substitute one problem. Think about it, fix a distribution. Look at the best deterministic algorithm for that distribution. Can that tell you something about me? Not need another one. So let's take expectation of this quantity with respect to this Q. This is true. Right? So let's take another expectation from the outside over Q, where Q is the distribution over sigma. Now there is an expectation over the COPT also, because it depends on sigma and sigma is distributed according to Q. I'm just taking a expectation of this quantity. So first of all, doing nothing essentially. I have some inequality. I'm just taking expectation on both sides with respect to the sigma, which was fixed here. Now, yes. No. There is no distribution. I'm given an input sigma. That's the cost of that sigma. Now I'm choosing a distribution. So how we should think about C equity sigma is for a fixed input, that's my cost. Now input itself is stochastically generated. Now the cost will keep changing. Take the average of that. That is what this quantity is. Okay with everybody? What this means? Right hand side. No model. Use some arbitrary distribution you're fixing for the moment. No control over what it is. Any Q. This is a valid quantity. It's a valid quantity. You come up with whatever Q you want. Now exchange this expectations. Assuming it can be exchanged. Tell me what happens. The right hand side remains, I'm not doing it. What is this quantity in the inside bounded by? What does it tell you first of all and what it means? So now use the observation I said, fixed input distribution and find the best deterministic algorithm for that. Does that have any bearing on the quantity on the inside?
UA.
This quantity. Sorry? No. There's no OPT here. All I'm saying is for this, assume that you know the best deterministic algorithm. Can you use that information? Yeah, you can remove the expectation with what? Yes. So that's the point. So let C star be that value. Let C star be, I'm without caring about mins, max, inf, soup, writing means you take that with a pinch of salt. Add my notation. D, C, A option. This is the quantity. Just not. So let's say C star is the minimum of that expectation or all possible deterministic algorithm. The well-defined quantity. Can I not replace that here? Because the C star should be smaller than this number. So C star is the minimum. So this should be smaller than this C star. And then there is an expectation from D, which is useless because I'm replacing one particular deterministic algorithm. So call this 1. Then 1 implies C star is less than mu times expected value of T. Everybody with me? I'm just replacing this with a smaller quantity from C star. Don't care. C star is a number. No. How do I go in the right direction? Right? This is less than. So if I say something larger, no, think of you're trying to do on the competitive ratio. So in some sense, finding the best online algorithm. So you cannot say find the algorithm who has the largest cost. You should always look at the online algorithm who has the smallest cost. Because remember, we are all doing minimization problem. All of this makes sense, and the overall objective is to minimize them. So maximum. It could be D. No, why D? This is a well-defined quantity. Sigma is an input, stochastic, according to distribution Q. A is the best algorithm for that input, which is stochastically generated. Now I don't have to worry about D. I'm not asking you how to find it. This is a very, very abstract objects going on. And I'm well over time. This implies that mu is greater than C star divided by expected value of Q of P. This is my lower bound. That's all. This is Rahul's recipe in 2 lines. But that one beautiful idea does the trick. That you fix a distribution of the input, find a deterministic algorithm which is the best for that input that relates to a lower bound on the competitive ratio of any randomized algorithm. That's the amazing. It doesn't tell you how to pick Q. Uncertain objects here. I don't know what this Q is. For any Q, this is true. So very important. For all Q, this inequality is true. So you choose a weird choice of Q, a good choice of Q. It just gives you different numbers. You have to find what is the largest such number. So for each Q you pick, you somehow have to find C star. That's the more difficult of it. You can always pick a nice distribution for which you can find C star and say, okay, this is my lower. But that's not going to mean much unless you pick the right Q and are able to find for that right Q what this number C star is worth. Think of this as a convert. You know what? No matter what happens, you will not come up with a randomized algorithm which can do better than this. That's spirit. It doesn't tell you anything about how to achieve it. You could actually, in the best case, the tightest bound might be even larger than this. It's giving you one bound. No guarantee that this is tight. But it's a very strong technique coming with a very simple idea. So I think you should stop here. Next time, what we will do is that this recipe gives us a bound of 1 minus 1 over E. And that is in fact top. So for this problem, this recipe gives you a tight lower bound, which is achieved. So yeah, the class is over. Feel free to leave. Q small degenerate. Input, right? It's an input distribution. Fine. So then my algorithm is, I can always tune it, right? That will come out to 1. So it's useless. Yeah. So the more richer you make Q, the better bound we should expect. Agreed, but now it's telling you a recipe. You choose a Q. I will give you a bound. Now that bound is tight or not, I don't know. No, Q and D have no relation to each other. Q is an input distribution. D is a distribution over online algorithms. They have no relation to each other. Mm-hmm. No, that is true for many problems. No, but I'm telling you that for many problems, you can actually characterize the offline optimal answer, but still doesn't carry over to the online case. It might be very specific to this problem. It's not in it's, now you're putting me on spot. Let me think. Caching, for example. Do you know what caching problem is? So you have a fixed size memory. It can store only K files. A new file comes in which is not part of this K, you have to eject some file and bring in this new file inside. So the offline setting, we know what the optimal algorithm is, which is essentially that file whose request is. So for that, you can characterize the cost. Still doesn't tell you, but your observation is more or less right that this key intel problem is a very, very simple online algorithm for which you're able to do certain things. Yes. I don't know. You do what you want. So nowhere all possible deterministic algorithms. Like there is some distribution. All of this, I never characterize. Here is my A1, here is my A2, here is my A3. For the ski rental, it turns out they're easy to describe. But in general, it's not easy to describe. This recipe works for everything. Yes, so you can essentially erase everything beyond P. So you can keep A1 through AP. Okay. Not possible at all because input is not one parameter input. In this case, the input is also one parameter. It just picks the length of the ski season. That's why it makes it easy. Input could be adaptive. Input could do crazy things. Depending on what you've done, it might suddenly change its track. So input is still allowed to be adaptive because it can see, it can actually simulate the algorithm and do what it wants to do. So don't confuse between Q and D. All of this is in the notes. So have a look. Q is complete different space. D is completely different space. Yes. Correct. No, this is a well-defined quantity. So fix a sigma. So sigma and a pi sigma is another sigma, right? That's a valid input. I'm taking max over both of them. So you don't have to do that. We think of the first sigma as sigma 1, permuted sigma as sigma 2. The denominator is not changing, but the ratio could be different. Any questions from the web audience?